Greetings, guys. All right, so we left off talking about synthetic division. Let's pick up with those problems again, work those out, and then let's get to the real reason that we wanted synthetic division and the purpose that we're going to be using it for, right? So I'm gonna continue here with x to the fifth minus 3x to the fourth plus 12x minus 33 divided by x minus 3. Okay, so just recap on synthetic division here. Remember, I'm going to be setting up something in the box, right? The guy in the box. And I'm going to put the number in here that causes the denominator to be 0, right? We're always going to have that linear denominator here, just x and a number, and I'm going to pick whatever number zeroes it out, and that facilitates the subtraction that division needs, right? Okay, and then over here I'm going to put my coefficients. Don't forget, I can't skip any columns, right? I've got x to the fifth, I've got x to the fourth, but then it skips straight to x to the 1. So I've got to fill in the rest of those columns in between the fourth power and the first power there. So here I go. X to the fifth has a 1, then negative 3x to the fourth, then 0x to the 3, 0x to the 2, 12x to the 1, and then negative 33 for the number portion, right? Okay, so then I put my 0 here underneath that guy. Got my line going all the way across. And remember, with synthetic division, every time you have a column ready to be completed, you're going to add, right? So 1 plus 0, got 1. And then anytime you've completed a column, you multiply the result by the box to get the intro for the next column, right? So 3 times 1 gives me the 3 that I need here. And then negative 3 plus 3 gives me 0. And then 3 times 0 gives me 0. 0 plus 0 gives me 0. 3 times 0 gives me 0. 0 plus 0. 3 times 0. 12 plus 0. 3 times 12, finally, right? 36. Okay? And then here I get a 3. All right. So that's how synthetic division is going to work. And then from here, remember, what we're going to do is we're going to start on the right-hand side. And we always start by counting from the remainder, right? The remainder is going to be that last spot always. And then I'm going to count up place values from there. The 12 is going to be your number. This is going to be my x to the 1, my x to the 2, my x to the 3, my x to the 4 power. And you'll notice we dropped a power, right? We started with x to the 5th. We've gone down to x to the 4th. That's just your division rules, right? X to the 5th, x to the 1, 5 minus 1, you're going to lose a power, right? Okay, so now that I have it organized, let's write out what the answer is, right? The division answer here, x to the 5th minus 3x to the 4 plus 12x minus 33 divided by x minus 3 is equal to 1x to the 4th plus 0x cubed. I'm not going to write that. We keep the columns here in the division, sure, to keep track of that, but I don't really need to write it in the answer. I have no x to the 3's, no x to the 2, no x to the 1 power, but I do have a 12 number. So I put plus 12, and then I have a 3 remainder. So don't forget, the way we handle remainders is like mixed numbers. I'm going to put plus the 3 remainder divided by the original divisor, x minus 3. Right? So there's my synthetic division completion there. Okay? All right, so let's do the next example. The next example is 3x to the 3 power minus 48x plus 25x squared plus 20 divided by x plus 10. And somebody, when they wrote this problem, thought they could slip one past you and get the old slip one going. Look at that. They transposed the x to the 1 and the x to the 2 power there just to see if you were paying attention. So when I'm writing out my coefficients, pay careful attention to the way the order the numbers are actually in. So in the box, I've got negative 10, because remember I've got a 0 at the bottom. Okay? And then for my coefficients over here, I've got 3, then 25, right, because that's 2, then negative 48, then 20, right? Got my 0 here, draw my line. And don't forget, when you're writing out these coefficients, you should be able to count down, right? This is x to the 3 power, so I start 3, 2, 1, none, right, for my x powers. And that's how I know I've filled in all the spots and they're in the correct order. Okay, synthetic division. Add, multiply, add, multiply, 50, add, 2, multiply, negative 20, add, 0. We got a 0 remainder that time, right? So we're not going to have the partial piece at the end anymore. This one actually divided out cool and even, right? All right, so 3x to the third minus 48x plus 25x squared plus 20 divided by x plus 10. Now let's count out our spots here, right? Here's remainder is in the first spot, right? This is remainder. So then this is the number. Here's the x. Here's the x squared, right? So the final answer on this one is x squared, 3x squared, minus 5x plus 2. No remainder, right? No partial piece at the end. Okay, later on what you'll see is this is going to be one of the divisions that we'll love to see. We love to see this 0 remainder here. This right here, whenever we have a perfect division, we like to see that when we're doing these types of problems. That's the ones we're looking for. Because I can do this. Notice I can actually multiply in this equation right here. I can actually multiply the x plus 10 to both sides. And it would look like this. 3x to the 3 minus 48x plus 25x squared plus 20 is equal to 3x squared minus 5x plus 2 times x plus 10. Okay? Now, just as a little hint here for what we're trying to get to is, this is what we really want, right? Synthetic division is just a tool, just a small way of being able to do divisions faster. The real depth, in-depth piece here that we're looking for is the fact that I have now just written a complicated polynomial as a multiplication of two smaller, less complicated polynomials. In other words, we just factored something complicated. Okay? That's our end goal here. We are going to be doing these kinds of divisions with this express goal of being able to break down large polynomials like this into smaller ones, which you've been doing for quite some time up to this point, right? But these are going to be polynomials normally that you would not have a express method for, like all those old school methods. Okay, so this is the gold right here. This is the piece that we're really looking for, being able to factor, and the division is the key to that. Okay, now the actual answer to this problem was here. I was just showing you a little bit extra there so we can get a little hint in there. But let's move on down to the next sample here. I want to show you a property. Okay. Now here's what I'm going to do. I'm going to take function, f of x, and set it equal to 5x to the 7th minus 3x to the 5th plus 2x squared minus 1. And just, for old school sake here, I'm going to ask you to do a simple function value here. What is f of -1, right? Don't forget that our function set up like this is such that the generic definition has the x, and if I put a number here, that means to input that number into x, right? So for this particular setup, f of -1 would be me doing 5 times -1 to the 7 minus 3 times -1 to the 5 plus 2 times -1 squared minus 1. And I know what you're thinking. What does this got to do with division? Hang on, we're getting there. Watch. Coolness, right? Okay, so look. -1 to the 7 is -1. Times 5 is -5. -1 to the 5th is -1. Times -3 is +3. Right? -1 squared is 1. Times 2 is 2. And then, of course, the -1 is still there. So all of this put together tells me that f of -1 is equal to -5 plus 3 plus 2 minus 1 for a total of -1. Now it's just a coincidence that that -1 and the -1 match up here. That's complete coincidence. Okay. Now, here's where the division comes in. Pretend for a moment that I want to do the division of the 5x to the 7 here minus 3x to the 5th plus 2x squared minus 1. Let's say I want to do the division of that by the polynomial, the denominator from before that would have caused us to put the -1x value, right? This is the key right here, the x value being -1. I'm going to divide by the thing that makes that x value the box number. So remember, if I were to put -1 in the box, that means I was dividing by x plus 1, right? Okay, so I'm going to do this division right here. 5x to the 7 minus 3x to the 5th plus 2x squared minus 1 divided by x plus 1. Okay, so let's do that division for a moment. So to do that division, I will put -1 in the box. Right? -1 in the box. And then my coefficients, don't forget, we need to count down and have all the spots. So I'm starting with x to the 7, I have my 5, but no x to the 6th. Then -3x to the 5th. Then no 4 or 3 power. Right? Then 2x squared. And no x to the 1. And then -1. Okay? So I put my 0. Draw my line. And I'm going to do my synthetic division now, right? So I add right here. This is going to be 5. Multiply. -5. Add. Multiply. Add. Multiply. Add. Multiply. Add. Multiply. Add. Multiply. Add. -1 times 0 is 0. -1 plus 0 is -1. Okay, now the division is done, right? Let's look at what we have. I want you to notice that the input value here is in the box, right? The top here represents the function, as it did before, and then look at the remainder. Notice it's the same as this output. Not a coincidence. That is absolutely not a coincidence. Okay? Now, sure, this seemed like it took more calculations than this up here. okay? But there's a link here, okay? As I mentioned before, we're going to be using synthetic divisions to factor, to break down large polynomials. Well, this is like the second bit of information that's going to help us on our journey, okay? When we're doing these divisions, this connection right here is going to at the same time tell me that I have an x-y pair when I'm looking at these polynomials as functions as well. So not only am I going to have polynomial functions, I'm going to be able to factor them with divisions when desired, and while I'm looking for those factorizations, I'm also going to get x and y pairs from each and every division that I do. So it's not a wasted division at any point. I'll actually have some sort of point on any function graph. Okay, so this is what we're going to call the remainder theorem, right? The remainder theorem states that if you use the number in the box as an x value, an input, right, then the remainder of this division can be thought of as a y value when the coefficients here represent a function. To further this along, okay, let me go back to a division that we just did a moment ago. Let's go back. Just a little bit ago, we talked about the division x to the fifth minus 3x to the 4 plus 12x minus 33 over x minus 3, right? Okay, so let's set that up again. We have 3 in the box. We have 1, negative 3, 0, 0, that's 5, 4, 3, 2, x to the 1, and number, right? Remember, this is the same division as before, so I'm just recreating our little wheel here. Okay, so there's the division that went along with that particular setup, right? Flip it around and let's talk about the remainder theorem. What if this was a function? What if I had g of x is equal to x to the fifth minus 3x to the 4 plus 12x minus 33, right? Then what function value would this division represent? Now remember, when I'm putting a number from the division into the box, I change the sign. But once the number's in the box, that number is an x value. So this is telling me right here that g of 3 for this function should equal 3, right? And again, that's a coincidence like the last one, the numbers are the same. But let's check that out. Double check here. Look, g of 3 is going to be 3 to the 5th minus 3 times 3 to the 4th plus 12 times 3 minus 33. Okay? 3 to the 5th just happens to be 243. 3 to the 4th is 81 times negative 3 is going to be negative 243. And then 12 times 3 is 36 minus 33. Notice these two zero out, right? And then 36 minus 33 gives me that g of 3 is in fact equal to 3. Again, the numbers being the same, the x and the y is just a coincidence, but it is not a coincidence that the input being the same gives the remainder output here being the same. So to reiterate, when we're doing these divisions, every single division is going to give me some useful piece of information. Okay? However, the divisions we really want, as I mentioned before, are the ones that have the remainder of 0. Those are going to be the key to doing everything that we're going to do with the end result problems that we're going to get through in these polynomial functions. Okay? Let's continue with another example here. show x plus 4 is a factor of f of x equals 6x to the 3 plus 11x squared minus 60x minus 32. Okay? So let's tie together what we've just talked about, the two different angles that we've just talked about, how the synthetic division can also show us factorizations when the remainder is 0. And let's couple that with the function part that we were just talking about with the remainder theorem as well, right? So to do this, I will perform a division that causes me to use this as my divisor, right? I'm actually going to do 6x to the 3 plus 11x squared minus 60x minus 32 divided by x plus 4. Okay? I'm going to perform this division, but I'm going to do it with synthetic, of course, right? So what goes in the box? -4, right? And then notice I'm not missing any place values this time. 3, 2, 1, none. So 6, 11, -60, -32. I put my little 0, draw my line. So I've got my division set up ready. Okay, so then add, multiply, -24, add, I've got -13, multiply, that's what, 52, then add, I get -8, multiply -4 and -8, I get 32, and I get 0, okay? So that's the key, right? Notice that I got this 0 remainder here, right? The 0 remainder. Since I don't have a remainder, I have shown that I can actually do this division evenly, flat out, nothing left over. So therefore, x plus 4 would have to be a factor, right? The answer to this division is here, equals this, right? Remainder, number, x squared. So this would be 6x squared minus 13x minus 8 is the answer to the division. Okay? Therefore, I can actually say 6x to the 3 plus 11x squared minus 60x minus 32 is equal to x plus 4 times 6x squared minus 13x minus 8. That's what we're really saying with these divisions here when that remainder is 0. Okay? This is something that they're going to call the factor theorem. Anytime the remainder is 0 in a division like this, then the resulting quotient multiplied by the original divisor is a factorization of the original polynomial. Okay? Now let me throw something else on top of this pile. I want you to remember also that we just talked about the remainder theorem. So all the while at the same time, this was originally a function, right? So look, this should be an input and an output, as we were just talking about. This right here is also telling me, if I put these two pieces together, that f of -4 is equal to 0. So I actually got two very big pieces of information here from this one division. I found out that I can write this as a factorization, which, by the way, no small feat, right? Try to factor this old school way, you'll have a lot of trouble. This doesn't fit any of your old factoring molds. So this is a factorization that you normally wouldn't have been able to do. We're expanding that skill set here, right? Good factorization. But, there's more, right? F of -4 is equal to 0 also because of this division. Why is that important? Well, remember, anytime y is 0, what kind of important point is that x value? It's an x-intercept, right? An x-intercept. So not only do we find factorizations, we also get x-intercepts for our graphs, which is very important because that's our end goal here. We're studying polynomial functions. I'm going to be breaking them down so that I can find these important points, and they give us a lot of important information about the shape of the graph. That's what we're building to here with this synthetic division. Okay? Synthetic division is just a small tool so that I can find all of this information all at the same time. Okay? All right, I have one more example. Show that x minus 6 is a factor of f of x is equal to 4x to the 5th minus 24x to the 4th minus 3x to the 3 plus 18x squared minus x plus 6. Okay? All right. Same kind of problem as before, right? Just a little bit larger, no big deal. Don't forget that what we're going to do here is a division. And we want to show that it is a factor. So what remainder are we looking for in our division? 0. That's right. So here we go. I'm going to set up the division. I'm dividing by x minus 6. So the number that goes in the box needs to be the opposite. I'm going to put 6 in the box. And then my coefficients, let's count them. 5, 4, 3, 2, 1, none. I'm not missing any. So here we go. 4, negative 24, negative 3, 18, negative 1, and 6. Draw my 0, draw my line. Synthetically divide. I'm going to add, multiply, add, multiply, add, multiply, that's negative 18, add, multiply, we get a 0, negative 1, 6 times negative 1 is negative 6, adds to get 0, boom, that's what we were looking for. That 0 remainder says everything, right? This guy right here, the remainder being 0, is like the good feeling that we're looking for in these problems every single time. Okay? So I just found out that f of 6 is equal to 0. Right? That's important because we just found an intercept of that complicated function. That's very important. But also, don't forget that what this just showed us is that I can factor 4x to the 5th minus 24x to the 4 minus 3x to the 3 plus 18x squared minus x plus 6. And I can factor that into what? X minus 6 comes from the box times, I've got remainder, number, x, x squared, x third, x fourth. So that's 4x to the 4th minus 3x squared minus 1 as my final factorization there. Okay? So this is the end goal of the division that we're doing. The whole thing revolves around being able to get function values and factorizations all in one division, hopefully, right? Okay, I hope you guys enjoyed it. Stay tuned.